Hi everyone. In this video we're going to cover data screening and I'm re-recording a lot of these lectures so that they're not live with me moving around. So instead of listening to me walk around class, you're going to get to listen to hopefully my very quiet animals. So this video is going to cover the basics of data screening, and then I have several other videos if you want to dive into doing an example of data screening in, let's say, R or Excel, because Excel is paired for my JASP group. And so let's get started. The purpose of data screening is to look really at assumptions. We're going to talk about assumptions globally today, look for outliers, look for error problems, because if you just take a data set and run your analysis, you're not checking first, did people complete the data correctly? Did people finish? Do they skip random questions? So it really allows you to explore the data to make sure that it is what you think it is. And so we're going to talk about this in a global way, and then when we get into each analysis, we'll focus in on what's specifically important for that individual analysis. So for example, we'll do all of the assumptions, but let's say you get into ANOVA, you might not do some of them because it's specific to ANOVA. And so this really allows me to figure out if my data is what I expect it to be. And that really breaks down into several parts. And so we're going to cover this big important rule, and then we'll talk about the order of operations here. So I call this the big important rule. It really should be like a neon sign that flashes about the difference between hypothesis testing and data screening. So hypothesis testing is the purpose of what you're doing. It's the research question that you're exploring. And traditionally, we're going to use an alpha level, right? So we talked about the difference between P and alpha in a previous lecture, but we use an alpha level of P less than 0.05. So we want values that are less than 0.05 because that's where most people would consider things statistically significant. That's kind of in flux right now, this question of using a strict alpha criterion, but in general, people tend to pick 0.05 because it's a nice balance between type 1 and type 2 errors. Okay. So that's where our hypothesis testing criterion. Now you can change that, you can make it 0.10, you can make it 0.01, but you have some sort of hypothesis testing criterion. But when we're doing data screening, we're going to use a different criterion. I'd say this is the number one thing that people miss in this section. And I have always learned to use a very strict criterion, because if you decide to remove people who are outliers at 0.05, that's could be potentially a lot of people. Or let's say you're looking at your homogeneity test, something like Levine's. Well, it's known to be fairly sensitive to small changes in variance. If that doesn't make sense, it will in a little bit. So what we're going to do is we're going to use P less than 0.001 because we want to make sure things are really wonky or really bad before we fix the data or delete people's data sets. So that means that the scores are less than 1% of everybody else, or they're so different from normal that maybe now it's time to fix it. So it's going to be really, really bad before we decide to fix it. And so this is kind of like if your car is having problems and you decide to wait until it's pretty much ready to explode before you fix it. Not all textbooks agree on this point. I learned this from the Tabachnik and Fidel, but if you're reading Andy Field, for example, he uses a criterion of 5%. So you can actually choose both of these, the hypothesis testing one and the data screening one. But for purposes of my class, we're going to use 0.05 and 0.001. Okay. Now, my long-standing joke about 0.001, especially when we were using SPSS, was that it was the New Kids on the Block rule. That if it was 000, which is one of their most famous songs, then it was bad. But anytime you see 000 and followed by more zeros or a number, that's when we'll decide that data screening is poor. So for hypothesis testing, we want the numbers to be very small for reasons discussed in a previous video, but we're essentially trying to show that the likelihood of no differences is very tiny. For data screening, we want the likelihood to be bigger than 0.001. because that implies that there really aren't differences. And we don't want our data to be different than normal. Okay? So we do maybe want our groups to be different, but we don't want the data screening the things that we should be getting to be bad. And this tends to be difficult for people to get because you're so used to hypothesis testing. So remember, in data screening, we don't want less than 0.001 because that would be bad. So we want greater than 0.001. Otherwise, we got to do something about it. Or we at least have to tell people, hey, this is bad, but there's not a whole lot we can do. Okay. So there's a specific order of operations, and I love to ask this is my favorite test question. So why do we have to do these things in order? Right. So we're going to start by checking for accuracy. Accuracy is things like people who typed in the wrong thing, or you asked them how old they were and they wrote the word 19 instead of numbers 19. So these are little problems with the data set due to participant error, computer error. So participant error, you let them type something, which I heavily would recommend avoiding because people will do all sorts of things that you don't expect. Computer error, so we've had studies where we use Qualtrics, which is online survey software, and we expect it to be it sort of automatically codes numbers as 1 to 7, but we had a scale that was like a -3 to 3. So we had to adjust that whole thing down, even though that wasn't really a problem with the computer, it just was like an automatic coding that we needed to fix. Missing data, so fixing and dealing with anybody who's got missing data points, excluding them, or maybe estimating their scores. Outliers, and then our assumptions. So the big 4 assumptions we'll cover is additivity, normality, linearity, and the homogeneity, homoscedasticity set. Now, what do I have to do them in this order? Well, each one affects the subsequent ones. Okay, until you get down here to the bottom. These don't affect each other, but they are affected by the previous 3. Okay. So if I have an accuracy problem, it can become missing data. If I have missing data, that's going to affect my outlier analysis. Those outliers really affect our assumptions. So each step affects the subsequent steps. So we want to make sure we do these in order so we aren't wasting our time. Okay. So when we're checking for accuracy, what we want to do is go through and check for typos. So just little problems that we might have with the data set. The most common one is going to be data values that are out of range. So if it's a 1 to 7 scale and they typed in 10 by accident. And so you can check your min and max values to see if they're within a range that you might expect. Another thing that you might see is people typing words instead of numbers, or people just entering numbers that don't make any sense. You can also think about reverse coding items. If you're using a scale, that includes reverse coded questions. Now, if I have those problems, what do? Well, you can fix them. So if you have the original data, let's say you magically have it on pen and paper, you can fix that mistyped data point. If it's the word 19 spelled out, you can go in and manually change the number to 19. But mostly, we're not omniscient, so we don't know what the data point should be. So if the person typed a 10, I guess I could assume that they meant 1, maybe. So in those instances, it's better to probably delete that data point, not the whole person, so not the whole row, just that one wrong data point, so that you aren't biasing your data by your assumption over what you think the number should be. Now, if you have it, on another sheet of paper, certainly don't lose that data. But if you're like we are, and we get everything from an online data source, we just kind of have to delete those bad data points because we just don't know what they were or what the participant meant to type. Now, when I get into accuracy, you can see now how that might create missing data. So if a participant on a 1 to 100 scale types 207, I have no idea what that's going to be. So I'm going to delete that data point. That one data point has now become missing data. So this is why the order of operations here. And there are 2 big types of missing data that we're going to look for. One's called MCAR, so missing completely at random. This is what we want. If we're going to have missing data, this is the type we want it to be. Or MNAR. Ooh, sneaky typo. Now, MNAR is missing not at random, which is generally caused by people skipping a question or missing a trial. You coded an experiment in ePrime or maybe Inquisit, and you forgot to include a trial, so they're all missing one. Or there are questions on a scale that everyone just declines to answer. So for example, there's this drug scale that we've used before that has a question, do you use drugs? People mark yes or no. Then the next question is, can you quit drugs when you want to? Now you're supposed to say yes, but if you've just said no, I don't use drugs, you don't know how to answer this question, because you could say yes, I can quit when I want because I don't do it, or you might say no because I don't do it, and so people tend to skip it because they write NA out to the side. So that would be missing not at random. There's a reason why it's missing. Generally missing completely at random is people who, like, you're clicking online and they just skip one. So when for MNAR, it may be the question that's causing the problem. So this was supposed to be MCAR. Good grief. Fixed a slide that wasn't wrong. Okay, it's probably caused by skipping a question or missing a trial. This is where I was going. MNAR is missing not at random. And it may be that question that's causing those problems. So if everyone skips a question about alcohol abuse, what does that imply about the data set? So what should I do with different types of data? So if it's MNAR, so not at random, you really need to figure out why it's missing not at random. So you can either exclude that question or eliminate the data, but missing not at random data is problematic because it's not random. And so you have to figure out why it got skipped. In CAR, if it meets a certain set of scenarios, we can replace that data with a special function. So in R, we're going to use the mice function that allows us to do multiple imputation. In Excel, we're going to use some mean estimation because that's the only kind of options we've got. So how much can I replace? And so that kind of depends on the sample size. So 5%, now this does have nothing to do with the 5% rule for hypothesis testing, but it's sort of like, it's one of those like gold standards that you see published places that says that, like, if you're going to import data, usually around less than 5% is okay, because it allows you to keep your sample size, which helps with power, but it doesn't unduly influence the analysis. So it'll help you in the sense that you'll get to keep your participants, but it shouldn't push your design one way or another by, adding 10 points to one group. And so that rule applies across. So we'll talk about analyzing by participant. So how much data is the participant missing? Or down, how much of that variable is missing. So we don't want to estimate more than 5% of the data for participants or for variables. And so this is why it's important to look at the data both ways. So a participant might be missing, 10% of their data, but the variable only missing 1%, but you still don't want to estimate that one participant. So that means you need at least 20 data points for a participant to be able to get a good estimate. And at least 20 participants for each variable. So if I have a very small sample, you're probably going to have to collect more data. And so when you do analyses like ANOVA, where you only really have like one dependent variable, you can't make participants up. And so yes, in ANOVAs, there'll be several columns of data because it might be the group number for the participant or their IVs, but you can't make up a participant's dependent variable because then you're literally making the entire thing up. So this 5% rule kind of keeps you from cheating. Okay. Now the question is, what should I replace? So how much? You got 5%. Now what? Okay. I always tell people, don't replace categorical variables, especially like which group they were in a grouped design, because you should know this. Or things like gender or political orientation. So generally, categorical variables are harder to estimate. Don't replace demographic variables. Don't replace missing not at random data. And so we're kind of limiting ourselves to continuous-ish variables, so interval or ratio data, where there only is about 5% of missing data happening. Okay. So how do I replace it? Now we have how much and what. Now, how. And some of the older ways that people used to use, ouch, to replace the data, the most popular way was mean substitution. This is a very easy thing to do, and this is what you'll do if you're working with Excel, because there just are not that many options for this in Excel or JASP. I'm hoping they'll get to it at some point, but it's easy. You just find the mean of that column and type in that number. Most people now, for like fancy analyses, really don't recommend it because it tends to reduce the variance in the data set. And generally that would lead us to a significant result. So we have to be very careful about reducing variance by adding in the mean. Another way to replace is using a regression analysis, and it takes that data that's given and estimates those missing values. So that's a more popular way now to do it. And really, the reason that people used mean substitution before was that not only was it easy, these regression type analyses were much more difficult, especially if you didn't have some of the programs like we do now. So, is there going to be a cat fight? Meow? No? Okay. So one of the problems with some of these older ways of doing it is that it's called conservative. Okay, so it does not change the mean values for each group because you're including the mean. So that is a good thing, but it does reduce the variance. And so if you estimate a lot of the missing data, reduction in variance will help you cheat, essentially. And so we don't want to do that. Some newer ways to replace data is expected maximization. And that's a multiple imputation procedure. And so if you're using R, we're going to use some mice, which is multiple imputation. And what it does is it sort of like guesses a whole bunch of times what the data point might be based on the row and the column, and then picks the most likely one. So it maximizes by picking the most probable answer. Okay, now that I've taken the cat out of the room, hopefully we can finish. So we were talking about the best way to estimate the data. Now let's talk about a very practical issue here. So non-completers. So people who start your survey and then quit, or those freshmen in our intro to psych studies. Let's say that someone quits a study and they have more than 5% missing. What we want to do is first take those people out. So we want to, that's missing not at random, but for a different reason. So we'll tend to break apart and take out those people who didn't finish or have more than 5% of the data missing, then look at the amount of data missing for each variable. So we're going to kind of cut this apart like a cake. And the first thing we're going to do is take off those bad rows. And by bad row, what I mean is people who are missing more than 5% of their data by participant, so across their row. And by taking those people off first, we've removed non-completers and maybe participants who are just missing too much data because they just can't click right. And then we'll analyze how much data is missing by column. And that'll allow me to look for MNAR data by column. So for example, we did a study where we just left a question off. Don't know why, but we did. About halfway through, I went, oh crap, and added it in. And so what that means is that even if a participant finished our entire study, they've now got a missing data point. But we don't want to estimate the data for that question because we left it off, not because participants were just screwing around. Okay. So we'll take off the bad rows. We'll take off the bad columns. We'll replace the data in whatever form we're going to use. Then we'll put the rows back and the columns back that we need to. So we kind of are taking it apart and putting it back together again. So you can also think about this like Legos. So we'll take off some Lego pieces, take off other pieces, and then we've got to put them back together in reverse order. Okay, so it's kind of like taking something apart. Like if you like to disassemble car parts, you have to put them back in reverse order. So this will be covered more practically in the examples on how to do this. And so once we deal with missing data, so we've either deleted the people who have too much missing data, or we've estimated the data, now we're going to deal with outliers. So outliers are people who have extreme values on one or more variables. So we have to replace missing data first, because if we're going to give them a score for this, one, if we're going to exclude them because they have too much missing data, let's just go ahead and exclude them and be done with them. But then if we decide to estimate a score for them, now we need that score in there to do this. Okay. So there's two options for outliers. We can do univariate analysis, where you're an outlier on one variable at a time, or we can do a multivariate analysis where you're an outlier for multiple variables. And so that implies that your pattern of data is an outlier. So, you might have been marking 7-1, 7-1, 7-1 on a scale, and so that pattern is very strange because people tend to mark 6-7, 6-7, 6-7. And so we'll talk about how to analyze both of these, because you'll have to do both depending on what type of analysis you're using. So mostly you can check for univariate outliers, but when you have a big data set, it's really easier to do multivariate outliers. Okay. So once you get into looking at ANOVA, you'll check for those univariate outliers by using z-scores. Okay. Right now we're going to talk about multivariate outliers. Okay. So multivariate outliers, what we can do is use Mahalanobis distance. Okay, so Mahalanobis distance is a distance of a person, so a case, each person from the centroid. Okay, a centroid is like the middle of the middle of the middle. And so if you think about the centroid as maybe the middle of town, and it measures how far apart each person is from the middle of town. So if you're trying to decide with your friends where to go to dinner and you want to find some place in the middle, you're thinking about the centroid and how far away everyone is from that middle. And so the person who's the furthest out is the biggest outlier. They're the one furthest away from you, finding some place in the middle for you guys to all go eat dinner. Okay. So we're going to look for when people are very far from the middle. Okay. Now this doesn't always work in Excel, but it is an important type of thing to know about because people use it a lot to analyze for outliers. So you may not get to do some of this analysis depending on which path you're taking. But you'll at least have heard of it before when it pops up into your articles that you read. And so the way that we check for Mahalanobis is that we'll create those scores, those d-squared scores, so it's a measure of distance. Okay. We'll take the chi-square values to find a cutoff score. So we're going to draw a line in the sand. For anyone who's outside this part of town, we're just gonna not even invite you to the party. So it's sort of like creating a point at which those people no longer get included because they're just too far away from everything else. Okay. To find that chi-square value, what you've got to do is use the degrees of freedom. Okay. So these degrees of freedom are different than the degrees of freedom we've talked about before, like for t-tests. Where it's based on the number of participants. These degrees of freedom are based on the number of variables, but only the number of variables you're testing. So you might have a gender column in your data set, but you're not going to use that to screen people because you can't really control their gender. So it's the number of variables that you are using to test them for outliers on. And then we'll find the point at which they're p less than 0.001 because we're doing the big important rule. And so we're going to use chi-square to do this because through previous testing, we know that these distance scores are chi-square distributed. So what that means is there's lots of small ones. So there's lots of people who are very close to the center of town. And then there's only fewer and fewer people as you get further away and you go outside of town. And so when you have lots of scores very close to zero and and then the scores, less and less scores happen as you get further from zero, that's a chi-square distribution. So we're going to use chi-square as our cutoff to match what we know about the way that Mahalanobis works. So if you're using R, you'll use the chi-square function. It will tell you that cutoff score, and you'll find a way to exclude people who are bigger than that cutoff score. If you're using Excel, you're more likely going to be using a z-score, some sort of z-score function. And so here's an example of what that looks like. So over here is our distribution. And as you can see, lots of scores close to zero and fewer scores as you get further away. The more variables you use, the more you expect people to vary, because that's just the way it tends to work. And so we'll use this p less than 0.01 column. But if you're using R, like I said, you'll make the computer do this for you, so you don't have to pull out a table every single time. But just an example of how this would work. The other thing that we can do is use it in a regression analysis. We can add two more pieces to that. So we can look at discrepancy. So discrepancy is a measure of how far away people are from the rest of the data. So scores can be very far away from the data. Like let's say you measure high school students on their SAT scores. So you might have a whole bunch of people who cluster around the average, and then a couple of students who maybe get a perfect score. They would be discrepant. They're far away from everybody else. There's kind of a break in the data. Okay. Leverage is a measure of how much each individual person affects the slope in a regression analysis. So what I think about leverage is like a jack on a car. So where you're trying to get leverage, and so you're jacking the car up so you can remove the tire. Let's say you have a flat tire. Leverage is how much you can get the car up off the ground. So you're changing the slope of the car or how far off of the ground it is. So a person who has a lot of leverage changes the lift of the car a lot. In a regression analysis, that's bad. Okay. And so leverage values are something that we'll use. A measure of influence. Influence is a measure of leverage and discrepancy together. So somebody who is really far away and changes the slope a lot is really bad. And those are called Cook's values. So it kind of depends on the analysis what type of outlier we're going to look for. So for ANOVA, it might be a z-score. For regression, it's going to be maybe discrepancy and leverage and Cook's. Or it might just be Mahalanobis. So it kind of depends on the type of program availability that you have and the type of analysis that you're running. So what do you do with these people that are outliers? So I'm an outlier, now what? So you have to ask yourself, did they do the study correctly? So if they did the study correctly, why are their scores so weird? Because we're making this cutoff where they're the likelihood of their data is less than 1%. Like they're really, really odd. So are they part of the group of people that you're really wanting to test? Did they really do the study correctly? I mean, I deal with the science of freshmen, and so I know they probably didn't do it correctly, or they're just screwing around. So you kind of have to decide how you feel about the way the data looks. I tend to eliminate them because that means if they're an outlier, their scores are really strange. But you can also leave them in. So you can do all this work and then decide that you don't want to eliminate them. But you did screen for them so people know that you had them in your data set, for example. In most of the assignments, it will tell you, take them out, leave them in. But if you're doing a real analysis, you would want to talk about how you screened for them, telling them, here I found this many using Mahalanobis, and we left them in because it didn't make a difference in the analysis. Or we left them in for power, like having a reason why you did what you did in your design. So once we do those big three, what we'll do is now we'll move on to assumptions checks. So those three have to be in order because they affect each other sequentially. At this point, not so much. So once you just have to do assumptions last. Now you won't always have all of these. It'll depend on the analysis, but we're going to, again, this is a global overview of data screening. So we're going to talk about how to look for all of them. And then within each analysis, talk about which ones are apply to the design that you're working with. So let's start with additivity here. Additivity is the assumption that each variable adds something to the analysis. So each one is additive. It is useful to add. Okay. Often this is sometimes called multicollinearity, but multicollinearity is the bad name. We're going to talk about assumptions and use the good name because we want to meet them. We don't want them to be significant. That would be bad. So I've said this, students have taken my other classes or have listened to more than 3 of these videos. You don't want something to be significantly bad for assumption testing. Okay, so this, if we break the assumption, it would be called multicollinearity, which would be bad. Okay. And multicollinearity is when variables are too highly correlated. So when they're that correlated, they're not each adding something to the equation. You're wasting your time because you've got 2 variables that basically tell you the exact same thing. And so when 2 variables are too highly correlated or more, it's no longer useful. It's no longer additive because each variable tells you the same answer more than once. So a general rule for too high is R is greater than 0.9. This is very, it changes based on the analysis that you're doing, but 0.9 is always bad. So if your variables are that highly correlated, it tends to bork your analysis. And bork is a very technical term that means that it might not run or it makes interpretation very difficult. Okay. So we don't want to use 2 variables that give you the same answer because that will lower power. It won't run or it might be a waste of your time. The error message that you'll get often says singular matrix or something about a Hessian matrix or something being not definite. Those are the most common versions of that theme. And that essentially says that the variables are too similar. So real life data example, working with a data set, went to reverse code an item, mistyped the variable name, and included both items, so the original and the reverse coded, and we kept getting this error message because those are the same item at that point. So a reverse coded item and a regular item are perfectly correlated, so it just would not run. Or also real life example, a student was working with a data set in Excel and accidentally cut and pasted a formula that made the entire column zeros, didn't notice till they tried to run the analysis, and if a variance of a variable is 0, it will also not run. So I've done both of these. So you have to have some variance to work with and it can't be perfectly correlated. Okay, so that's additivity. We want additivity by not having multicollinearity. So when we get into this next part, there will be diagnostic plots built into the analyses, especially if you're working with JASP. But what we're going to do is use this analysis to just screen anything. So once you learn this set, you can apply it to all these different types of analyses. And so we'll do most of this in either before you start in R or in Excel if you're working with JASP. And so this is, again, just sort of a global picture with the warning that like as we go through the semester, you'll see some other options that are possible. So when we're running an ANOVA, t-test, correlation, any of that kind of categorical data, minus correlation there, we're going to run a fake regression. This is a fake analysis because it's not the real one. And so this fake analysis purpose is to just to get the numbers you need for data screening because they're not automatic. So we're going to run this like fake side analysis to be able to see the numbers we're interested in. When you get into a regression-based test, like hierarchical regression, you run the real regression because you are running regression. So once you get to regression, this will be just tweaked just a little bit, but kind of a warning, I'm going to talk a lot about fake analyses, and I call it a fake analysis because it's not really our hypothesis test. It's a vehicle to get the numbers we need. Okay, so we're going to make a random variable, and we're going to test that against chi-square. Okay. So we're using our fake analysis, and we're creating these random variables, and you'll see this when you run one of the examples. And we're going to compare this fake analysis with this random variable to chi-square. And so it's going to feel very strange because we've made up a random variable in our fake analysis, and then we're comparing it to this other apparently random thing. Okay. And so the reason for this is that the assumption tests that we're getting to, normality, linearity, and homogeneity, skedasticity, what we expect is a chi-square distribution of the errors. So we've already kind of talked about this a little bit, but the errors are like how off we are at guessing. And so we want lots of small errors. So this is our center of our center. We want lots of people close to the middle of town and only a few big errors. And so that's a chi-square distribution. Okay. But those standardized errors, so we're going to take that error, we're going to standardize it. So we're going to z-score it. By standardizing it, we kind of make the whole thing nice and normal. So we expect it to be distributed around 0. So some people are close to the south side of town, some people are close to the north side of town, but they're still close to the middle. And so we want the error, the actual error, to be chi-square distributed. But once we z-score it, what will end up happening is that it will turn out to be a normal distribution. Because chi-square and normal actually are very similar to each other. But what the heck is this error thing? What we're going to do is create a random variable. And that random variable, like I said, is a vehicle to get the numbers we need. And so we're just going to make it up. And then we're going to use our data to predict a made up number. And so what that does is it shows me the variance in the data set. So is the data linearly related? Is the data normal? I'm predicting this random number, so we would expect a prediction of a random number to be random. So a bunch of the errors are going to be small, and only a couple of errors are going to be large. Okay. And so we're making up a random number, like I said, it's the way to get the numbers we're interested in, which are these error terms. And we don't really expect these error terms to be anything in particular. Like, I don't expect, person C to be 2 points off. What I expect is across the whole data set for there to be people who are just a little bit off, because we're predicting randomly here, and only a couple of people to be very off. And then when I standardize those sets of numbers, they're going to be really close to 0. And the further we get away from 0, the worse that is. So for each of these assumptions, there are ways to do this in a univariate fashion and a multivariate fashion. I'm going to teach you the multivariate fashion because it will always apply. But if our multivariate data assumptions checks end up being bad, I might then tell you to break apart the univariate pieces and see which variable is bad. Okay. So let's start with normality. Okay. The assumption of normality is that the sampling distribution is normal. Okay. This is tricky. It's not that the sample is normal, your data, your people that you have. And it's not that the population is normal. Okay? It's that the sampling distribution, the step in the middle, is normal. So a sample is the people that you collected. The population is the people you collected from. So I might be interested in everyone who speaks English as their first language. I took a sample from Missouri State freshmen. So my group of participants is, intro to psych students, but my overall population is everyone who speaks English as their first language. So those are very different things. Okay. A sampling distribution is this mathematical tool that allows me to examine my sample as if it were the population. And so what happens is we pretend to take lots of small samples of the size of our data set and use that to create things like standard error and just to test our analyses. So I am not the best at explaining sampling distributions without just this giant whiteboard and lots of scribbling. So what I tell you to do is watch the best way to understand sampling distributions. There's a video called Distribution Bunnies. It's linked on Blackboard. If you are not one of my students, you want to watch this, you should Google central limit theorem bunnies. It'll be like the first thing that pops up. And it explains how, as we get more and more people, the sampling distribution, which is lots of mini small samples, becomes normal, and that is what the actual assumption is. So it's assuming that the sampling distribution is normal, which is our way that we use a sample to estimate the population. Okay. So for multivariate normality, what we're assuming is that each variable and all the linear combinations of those variables are normal. So if I have 10 variables, each variable is normal, and each one of the combinations. So 1 and 2, 1 and 3, 1 and 4, 1, 2 and 3, 1, 2 and 3 and 4, etc., etc. Okay. But the central limit theorem, which is where you should have paused and watched the distribution bunnies video. Okay, so the central limit theorem is this idea that as the sample gets larger, it becomes more normal. Suggests that if I have at least 30 people, the test is robust to violations of normality. Okay. So what that means is if I have at least 30 people, we can assume that the sampling distribution is likely normal. Okay. The sample may not be normal, the population may definitely not be normal, but the sampling distribution, where we're plotting the means of the data rather than the people, is likely normal enough. Okay. And so the test is robust. A robust test means that the sample can be non-normal and you'll still get the same results. So a robust test, I always think about those as flexible people, meaning you can bend them and they don't break. Okay. And so most of the tests we're going to cover in this class are robust to violations of normality, especially if you have 30 people. Okay. Now this isn't a rule that like 30 people and you're good enough for your analyses, so we're going to talk a lot this semester about power. What I'm saying actually is that at 30 people, normality is kind of okay. Even if the test that we're going to look at in a little bit isn't quite okay, it's robust enough to the violations that your answer will be the same whether or not the data is normal. Okay? What we're going to do is actually check the sample, because you can't really test the sampling distribution because it's this theoretical idea. If I have at least 30 people, you know, as long as if the data looks bad. If you have less than 30 people, like, you just gotta try harder, because 30 people almost never gives you enough power, which is a different subject altogether. But if you have less than 30 people and this check looks bad, you may consider changing analyses to some non-parametric design or that doesn't care so much about normality. So the issue here is, like, if you have enough people, you still want to check this and hope it's okay. If you don't have enough people and the analysis looks bad, you really got to reconsider maybe ANOVA. So what we'll do is create a histogram of those standardized residuals. And the standardized residuals, remember, are how much error you have. So you're measuring the distance from everybody from the middle of town. So how far out is everybody? And so you want lots of people here close to 0, so here in the middle, and you want the numbers to be mostly spread between -2 and 2. Okay. This is not a rule. This is just a general practice. So -2 to 2 is kind of where most of the data should fall, because that's the center of town and out. And so you want the data to be stacked above 0, so centered around 0 between 2 and 2. You would say the histogram looks bad if it doesn't meet those criteria. So if everything is shifted to the left over here, which would create positive skew, or if the data goes from -2 to 15 or something. So mostly you want to look for, is it centered over 0, and is it between 2 and 2? Okay. Those are your general rules for reading these graphs. There's no magic number to look at here. It's a little bit of a tea leaf reading. The next assumption we're going to talk about is linearity. Linearity assumes that there is a linear or a straight line relationship between two variables and their combinations. Okay. This gets a little weird when you're dealing with categorical variables, but we assume that the variables are linear and not curvilinear. Okay. And so we're going to look at a QQ plot, or if you're using JASP, a PP plot. They're the same thing. So theoretical quantiles or theoretical probability something plots, but every time I say PP plot, I get a little giggle because it's funny, but QQ plots as well. And what it does is it takes each person's data points, depends, and looks at where they fall in like a probability density area. And it maps them onto either quantiles or probabilities. Either way, generally on the bottom, what you'll see is -3 to 3. You want, again, most of the data to be on the line here between 2 and 2. So back to our 2 and 2 rule. And so you want the data to be pretty close to the line. This is where you have to be nice to the data. And so this deviation up here is not a super big deal. What you don't want to see is a hammock, right? So a big curve or a sort of S shape where it's above over here and below over here. So when you're answering these questions on an assignment, explain your thinking. Because these are the ones that are hard to grade because this plot is clear. The dots are on the line from 2 to 2 is how you'd answer. So you say, yes, it meets the assumption of linearity. But if you decided to be very persnickety about this area up here, you could say, well, at 2, the dots aren't on the line anymore. At least then we can give you partial credit because you're right, they're not on the line, but mostly this is a pretty good plot. So be sure you describe your thinking when you're answering these questions. Now, for the homogeneity and homoscedasticity, let's talk about what those mean first. So homogeneity stands for equal variances, so homo for equal, geneity for variance. So our variables or our groups kind of have roughly equal variances, so it's not like one group is variance is 10 and other ones is 100. That would be bad. Homoscedasticity is equal variance spread across the variables. So it's not really like variable 1 has equal variance of variable 2. That's homogeneity. Homoscedasticity is where variable 1 has equal variance at all points on variable 2. And so it's kind of like if you created a scatter plot of these two variables, it's not like the variance is really small on one end and really large on the other end. We're going to check these together with the same plot using a residual scatter plot. So we're taking people's fitted values, that predicted score for our person in our regression. Now this should be random because we created a random variable and we predicted our data with this random variable. And so each person's predicted score is random, right? And their error terms are also random, but often very small and close to 0. And the residuals are the difference between the person's score, the predicted score, and their actual score. So in regression, you might see that as y minus y hat, where y is their real score and y hat is our predicted score. Okay. So we're going to plot their predicted scores against their error terms. And what we want to see is a random smattering of dots, because we created a random variable and we predicted it with our analysis. So this whole thing should be random and centered around 0. And so when we look at these, what we should see is a bunch of dots. Okay. And so those residuals should be randomly distributed. Okay. And so it should just look like dots. So let's look at one of these. Okay. So here's an example of a residual scatter plot where we've got our fitted scores on the bottom, which we z-scored to ease interpretation, so to keep everything in the same scale. So you'll notice that all these plots have the same 0, 2 to 2 kind of interpretation. And then our standardized residuals over here on the y-axis. So what we want to do is see most of the dots cluster around 0, but evenly around 0. So for homogeneity, what we want to do is look at the spread across the bottom. And so the spread should be equal. It might be 3 to 3 and not just 2 to 2, but the spread should be roughly equal across the bottom and across the side here. Okay. So mostly everything should be centered around 0. This is where it shouldn't look like it's raining, where there's a line of clouds, 0, and then there's a big spread on the bottom. Or it runs from 2 to -8 over here. So we want an equal spread around 0 for homogeneity. Which is what I think this slide says. Whoops, nope, just kidding. So that slide does not say that. So an equal spread around 0 for homogeneity. Now for homoscedasticity, ignore the lines. What you want to do is draw a line around the dots, like an imaginary line around these dots, and you want it to look like a blob. So this is starting to become problematic because it's starting to make this square. So what we don't want to see, not square, that's a triangle, is shapes in the data. So we don't want it to start small and then get larger. So I'm going to cut away from my notes for a second and show you, and if you want to look at more of these, this is pretty easy to Google. So I'm going to Google heterogeneity, which is the bad term, instead of homogeneity. I'm going to click on images. And let's do scatter. See if we can get those scatter plots. Here we go. And so we don't want the spread to be small on one end and large on the other. And so we can kind of see that in some of these plots. Maybe I'll just type homoscedasticity. Here we go. This will be better. All right. Okay. So here's an example of a bad one. Okay. So the dots are small here and spread out large here, so it creates this kind of cheerleader megaphone shape. Here's one from a textbook, right? So this is very, it's centered around 0 and it's even all the way across. Okay, this one would be curvilinear, so you don't want this shape either. But here's a dot, centered around 0, but it is not homoscedastic because it makes this sort of triangle shape. So the joke is no cheerleaders, so no megaphone shapes. Okay? And this one would be a real hot mess, right? So you don't want the data to create sort of bulging shapes, or Dorito chips is another way you can look at it. So no points at which the spread is not even all the way across. So I always tell students to do is imagine or draw literally a line around the dots, and you want the dots to create this nice kind of blocky square area, okay, where they don't, ooh, here's another really bad one, right? So they're really close together here, and then the data spreads out really wide. Okay. That would be bad. Okay. You can also use this to, let's say, look at QQ plots, if you want to look at some of those to see nonlinear designs. Right, so they didn't standardize the bottom here, but that's really not good, that kind of curve there. This one would be pretty good over here. This one would be really bad. So none of the dots are really ever on the line, and it creates one half that's lower and one half that's higher. So the good thing about Google here is that you can find some examples of plots to look at that sort of help visualize this stuff. So here's an example of some nice normal histograms. Here's an example of a really poor histogram. And so you can look at a bunch of these different examples until you've seen some of them, and you can kind of guess which ones are going to be good and bad. Okay. So one last slide here, mostly for my R people. No, this is also true for my JASP Excel people. So this should say Rexel tips on the top here, but you will end up creating multiple data sets. So in Excel, you're going to make multiple tabs so you can keep track of what you've done across the data sets. In R, we're going to create little new saved mini data sets in our environment. Okay. As you go, though, be sure you use the last created data set. So don't use your master data set when you get to assumption testing, because why did you go through all that outlier stuff otherwise? Okay. And sometimes nothing breaks. The world is beautiful. There are no outliers. Okay, so you would just skip that step. Okay. So if there are no outliers, your no missing data set or your no typos data set is the same thing as your no outliers data set. Okay. So this will take a little bit to get used to. Don't get discouraged. You'll have to practice this procedure a couple times to get the hang of it. But you will end up with sort of multiple tabs, and that purpose of that is to keep track of where you're going. So I know that I've done step 1. Now let's move on to step 2. Oh, she asked me how many outliers were there. Well, in step 2, I had 50 people. In step 3, I had 47. So there were 3 people out that were outliers. And just allows you to keep track of all the things that you've done in your analysis so that you can report it later.